Hello everybody, back again to electrical and electronic circuit analysis. This is module 4, which is BGT and feed biasing. You remember we discussed BGT biasing, DC biasing, okay? We are going to discuss now feed biasing, but just as a comparison, in BGT biasing, what we did, we either use calculational method or graphical method. Calculational method, we go through the calculation of IB multiplied by beta to find IC, then we go for VCE, and then you can find other voltages in the circuit. And for graphical methods was load line analysis, where we started from the input characteristics, the relationship between I base and V base emitter, and we take the results, we go to the output characteristic, which is I collector with V collector emitter, and then we find the quiescent point. And after that, if we want to find any voltage in the circuit, we can easily. Now, with feed effect transistor, it's preferable graphical. If we have enough information, we can go for graphical. So here we are going to discuss different method. First of all, also similar to any other semiconductor devices, feed effect transistor have a family. We have GFET, MOSFET, deep feed, depletion layer fit, okay, and the difference between them in their characteristics, which is related directly, the differences become a function of insulation between the channel and gate. So based on the manufacturing, how we manufacture the type of insulation between channel and gate, we have different type of field effect transistor, and then we have different type of characteristics, and this means that we have a wide range of applications. As you know, GFET is the type of separation between junction and base and the body of the transistor is reverse bias p-n junction, while in MOSFET the insulator used is SiO2, and in depletion dipped fit we use formally full depleted layer, and this is have many applications in sensor, amplifier, memory, and so on. Now you remember also the relationship for input and output, between input and output, IDS against VGS is linear relationship because of the square in the equation, Shockley equation, and this will be used to graphically to find the quiescent point and find other voltages in the circuit. Okay, so it's preferable to use a graphical method if you can, and then you find the quiescent point and you find other voltages in the circuit. Also, just to remind you, the BGT controlled by current, while feed controlled by voltage. Here you can see, okay, just 1 second. Here you can see IDS against VDS. We remember this curve. We remember this. This is the cutoff region, and this is the linear or triode region. It's work here. The transistor work as a amplifier, and here is the saturation region for different voltage of VGS. And last session I've been talking about the relationship between ID on the output and VGS on the input, relating input and output. The curve is here, as you can see, is nonlinear, it's parabolic, because we have square in the equation, Shockley equation. And if we let me say distribute the region, then this part here is the nonlinear, or it is the linear region, which is triode region, and here is the saturation region, and here is the red one here is the channel off, or let me say cutoff region. Okay, we are going to use this curve to analyze the circuit, feed circuit. What type of circuits we are going to discuss? For GFET we will discuss fixed bias, self bias, voltage divider. For depletion, self and voltage divider. For enhancement, feedback configuration, voltage divider. We are going to discuss them, how we solve the equation to find the quiescent point. Now, first of all, if we look to the circuit, this is fixed bias. We can distinguish because we have two resistances, RD and RG. This is here the supply VGG, and this is here VDD. Output here and input here. First of all, IG is 0, always 0. Why? Because the gate is insulated from the circuit, so there is no current follow through it, and ID equal IS directly. Okay, current following here is the same current following here. Okay, And we have for depletion type, this is the formula. We discussed this in the last session. And for enhancement MOSFET, we have this formula. Two formula we can use. It depends on the type of FET we are using. Okay. Now when we come to do the math here to find the quiescent point, as you can see here the resistance is short circuit, okay, a short circuit resistance, okay, and the capacitor is open circuit here, okay, sorry, open circuit here, open circuit, okay. Okay, so as you know here, since the current IG is 0, there is no current flow in the gate because it's insulated. There is no open closed circuit. There is open circuit. Since no current flow in the resistance RG here, there is no current flow. So the voltage across it 0. It's like a wire, short circuit. So only this supply connected, as you can see here, this supply connected between gate and between the ground. Okay. Now from here, we can't, it's very easy, small circuit, we have only two voltages, this voltage and this voltage. So in this closed circuit, we can see the relationship based on Kirchhoff voltage law, minus VGG minus VGS equals 0. Very simple circuit. So VGG equal minus VGS. We can find VGS by multiplying VGG by minus. This is fixed bias. And if we substitute in the equation here, okay, and substitute it, we can sketch the relationship. Now here to plot, okay, ID, this is the curve we are looking for. Again is VGS here, VGS, okay. If we want to plot it, okay, we will make a table. Table contain only 4 points, no more, enough to sketch the curve. The curve will be between IDS or ID and VGS. This is on the output and this is on the input. Now when VGS is 0, the full current will follow across ID, which is IDSS. While when the current is 0, the full voltage appear across the transistor. So here we specify these 2 points where it start on what is end, where it is end at ID, where it is end at VGS. Now we need 2 more points. The first one is when IDS is half, the voltage VS is 0.3 VP. And when IDSS is 1/4, IDSS, this is ID, then VGS will be 0.5. These are the points we need to remember and to use them in the table. When we got them, we have point, let me say here, we have curve. Okay? Now for fixed bias, how we find the quiescent point? It's very easy. We said that VGS equal minus VGG. This is from the circuit in the previous slide. So we have here VGS. We make a line, vertical line, and intersect here with the curve. Then the line equivalent here give me ID. Since I got ID, I got everything. You see how easy it is? It's very easy. We just build our table here, sketch the curve. We have VGS because minus VGG for this circuit, fixed bias. We make a line, intersect here, and then the equivalent ID is in the front. By the way, almost the same curve, the same way will adopt, but different way how we intersect with the curve. The method depends on the type of circuit. This is fixed bias, still with fixed bias. Now if you look here, the distribution of voltages, as you can see here, here is VDD, ID. Drop here is ID, RD. If we subtract, we got the voltage here. VDS is the voltage between VD and VS. Since VS connected directly to the ground, so VDS equal VD. VGS already we got it. This is all this distributed here. Okay? You see, it's very simple circuit. No difficulty here. We just need to follow the procedure. For that, this is exercise for you to work on it. I gave you here VD, VDD, and I gave you RD, I gave you RG, and here is the voltage, and I gave you two important values, IDSS and VP. See VP in minus. For that, we are working to the left side of the graph. He asks you to find voltages, everything. It's very easy to follow. Okay? Another exercise you can follow here. Now we go for the next circuit, self bias configuration. Okay? Now what I will do here, I will add resistance here, RS. Okay? Definitely capacitance is to be separate here because this is DC as we mentioned before. Okay? And we have only one source in the circuit, which is VDD.